Welcome once again in the data communication lecture. Today we would be learn about the source coding theorem. So in the last lecture we have learned about the entropy, mutual information and properties of the mutual information, as well as we have learned the Shannon-Hartley theorem and trade-off between the SNR and the bandwidth. Now today we start the coding techniques. So in this particular unit we have to be learn two types of the coding as per syllabus. One is Shannon-Fanon, another is the Huffman, and both are the source coding theorems. So basically, coding offers the most uh, significant application of the information theory, and the main purpose of of the coding is to improve the efficiency of the communication system in some sense. So actually we perform the coding, source coding, for improving the efficiency of the communication system. So you can say a coding is a procedure for mapping a given set of messages. For example, I have given here x1, x2 up to xn into a new set of encoded message that is represented with C1, C2 and Cn in such a way that transformation is one to one from message or source symbol x1, x2 to the encoded message C1, C2 like this. That should be transformation should be one to one. That means each message there is only one encoded message. For each input message there is one encoded message, and this is called source coding. Okay, so this is basically a definition of the source coding. So in this source coding technique, whatever the code words would be generated, so the code words of this code dictionary are of different length, maybe uniform length, maybe non-uniform length, and whatever the efforts are directed towards getting the minimum average length of the code, resulting in increased efficiency of the transmission. So our main purpose of coding is what? Our main purpose is to improve the efficiency of the communication system. So for that purpose, we use the coding techniques. Some are having the uniform length code, some are having non-uniform length code. But our main purpose to improve the efficiency, and for that purpose, whatever the code word would be generated, its average length should be minimum. If the length of code word would be minimum, then its efficiency would be increased. So for source encoder to become more efficient, we require the knowledge of statistics of the source. Whatever the source we are using here to generate the messages, so we have to know the statistics of that particular source. Then and then only we would be efficiently encode that messages that is coming from the source. Okay, so uh, if you would be further explore, in particular, some source symbols are known to be more probable than the others. We have learned the probabilities in this particular unit. We know that every message having the different uh, probability of occurrence. So similarly here, some source symbols are having more probable than the others. That means we may exploit this feature in the generation of the source code by assigning uh, short code words to frequent source symbols. Those uh, source symbols that is having the more probabilities, we would assign them short quotes words, and those source symbols having the less probability, we would be assigned them as a long code words to the rare source symbols. So frequent source symbols would be assigned as a short code words, and rare code symbols would be assigned as a long code words. This is generally a way for encoding the source symbols. For this purpose, we refer as such a code word that is having the variable length code. And for this, there is a very famous Morse code. Morse code is an example of variable length code word. In the Morse code, the letters of the alphabet and numerals are encoded into streams of marks and spaces that is denoted as either dots or dash. So in the Morse code word, what happens? It is an example of variable length code word, first of all. Second, whatever the alphabet generally we use, like English alphabets A, B, C, D, or maybe the numerals 0 to 9, that is not represented in the directly into the Morse code. It would be represented in the help of marks and the spaces, and that is nothing but with the help of dots and the dashed. So we would see the example of the Morse code here in the particular slide. We can see for the alphabet A to Z, there is a Morse code is written in this particular table. You can take the screenshot of this particular table of the Morse code. Okay, so if you would be see here, in this particular Morse code, you can see, and whatever the numbers are written in below of this A, B, C, D, these all are the probabilities of this particular Morse code. Okay, of this alphabets actually. A having the probability of 0.08, B having the probability of 0.01, like this. And you can see like alphabet A is represented with the help of a dot and a dash. At the same time, E is only represented by a single dot. So if you would be observe all this, Q is having the maximum length, that is 3 dash and 1 dot. Okay, some other are also similar length like Y. So these are the rare using symbols in the source encoding. Okay, so these are some examples that basically we use for variable length code word. Now we have to be see what are the functional requirements when we would be use the source encoder, how we have to be encode the source symbols. So there are basically two functional requirements. First one is the code word produced by the encoder are in the binary form. So we are actually learning here a source coding technique or source encoder that is in the binary form. Second functional requirement is the source code is uniquely decodable. This is very important statement. Your source code should be uniquely decodable so that the original source sequence can be reconstructed perfectly from the encoded binary sequence. Why it is required uniquely decodable? So that when we have to be reconstruct this symbol at the receiving end, it should be perfectly encoded into the binary sequence. Okay, so now we have to be see the example of fixed length code and a variable length code. Now here you can see that in the table there is a two columns. One is for the message word, another is for the code word. In the message word, we have taken four message symbols x1, x2, x3, and x4, and all these four message symbols would be encoded through the source encoder, and the code word would be generated. Code word would be having the fixed length. Means there is only two bits are used for encoding this 0, 0, 0, 1, 1, 0, and 1, 1. At the same time, we can use a variable length code also for the same message symbols. So in this particular example, you can see we have used a variable length code. For the same message symbols x1, x2, x3, x4, we have the variable code word, length code word, like x1 is represented as a 0 only, x2 is represented as 1, 0, x3 is represented as a 1, 1, 0, and x4 is represented as a 1, 1, 1. Now we would be see what is the significance of representation like this variable code word and fixed length code word. That would be coming from the functional requirement. That is, first one is it should be in binary form, and second is uniquely decodable message. So for this purpose, we have to know the knowledge about the prefix coding. There is a one term used, prefix coding, that is used for all uniquely decodable code words. So to understand the concept of prefix coding, we have to be consider a discrete memoryless source, which is having the source alphabet x1, x2 up to the xk, and the source statistics as in terms of probability p1, p2 up to the pk. Okay, so these all source symbols from x1 to xk having the probability p1 to pk respectively. So for a source code representing the output of this source for the practical use, the code has to be uniquely decodable. This is, again I am saying, it is a most important property. If it would be uniquely decodable, then and then only we can recover the actual message at the receiving end. So this restriction means uniquely decodable condition or restrictions ensures that for each finite sequence of symbols emitted by the source, the corresponding sequence of code words is different from the sequence of code words corresponding to the any other source sequence. Okay. So the restriction of uniquely decodable condition ensure us that each finite sequence of symbols having the code word that is different from the sequence of code words that would be maybe corresponding to the same other source sequence. Suppose there is a two sources, one is a and x and another is y. Both are generating the source symbols up to the kth term, but at the receiving end, if it is uniquely decodable, then you can identify easily which is coming from the x source and which is coming from the y source. And that is done with the help of prefix coding. So we are especially interested in this special class of codes that satisfy these restrictions. That means all the code words should be uniquely decodable. It is known as prefix condition. So now we have to see how to use this prefix condition. So let kth code word assigned to the source symbol xk, that would be denoted by mk1, mk2, mkn up to this kn value, where the individual elements mk1, mk2 up to mkn are either binary 0 or binary 1, and n is here the code word length. So the initial part of the code word is represented by the elements mk1, mk2 up to mki, and this is a very important condition, that the value of I should be always less than n or maximum equal to n. So n is the code word length. So the value of initial part, that is up to the I, and I is always less than n. That means what? Suppose a code word is having the code word length is 10. So here n is 10. So the value of I should be either 9 or maximum up to 10, not more than this. So suppose for this 10-bit code word length, up to the first 9 bit, it is considered as a prefix. Or maybe first 5 bit, it is considered as a prefix. So we would be see what is the concept of the prefix. So any sequence made up of the initial part of the code word is called the prefix of the code word. So a prefix code is defined as a code in which no code word is the prefix of any other code word. This is a very important statement and the definition of the prefix code. Again, I am saying a prefix code is defined as a code in which no code word is the prefix of any other code word. No code word is the prefix of the any other code word. So we would be see this example to verify our statement that we have already given, that in a prefix code, no code word is a code in which no code word is the prefix of any other code word. You can see here, these are the 4 symbols x1, x2, x3 and x4, and that is having the probability. We have arranged these 4 symbols of decreasing probability, that is x1 having the highest probability 0.5, then x2 is less than this 0.25, and then further 0.125, x3 and x4 having the same 0.125. Now there is a 3 different coding systems has been shown here: code 1, code 2 and code 3. Okay, now we have to be identify that which is the prefix code. So if you have to be see code 1, the x1 is will be coded by the only 1 bit binary 0. So it is a code word for x1. Similarly, x2 has been be coded by only 1 bit binary code word, that is 1, binary 1. So it is again a individual code word. But if you have to be see the x3, that is encoded with the 2 binary bits like 0, 0. So you can see that this first 0, it is a prefix of this x3 code word 0, 0, and this is also the code word for the x1. Means what? This is x1, that is a code word 0, binary 0, is also appearing as a prefix to the binary code word for x3. That means it is not a prefix code word, because our statement is very much clear that it is a code in which no code word is the prefix of any other code word. But here in the code 1, x1 would be become a prefix of x3. So it is not a prefix code. Now we have to be see into the code 3. Again, same thing is happening. The code word for the x1 is 0, and if you have to be see the x2, that would be encoded with 0, 1. So here 0 would be become again a prefix of the x2, x3 and x4 also. That is also not a prefix code word. Okay. Now we have to come to the code 2. In this particular code 2, here x1 is encoded as 0, x2 is 10, x3 is 110, and x4 is 111. Now you can see neither of the code word is used as a prefix for any other code word. That means it is satisfying the condition of prefix coding, that it is a code word could not be used as a prefix for any other code word. Here in the code 2 section, neither of the code word of x1, x2 or x3 or x4 is used as a prefix for any other code word. That's why it is a correct example of the prefix coding. Okay, so this is very important discussion. I hope all of you have noted down or taken the screenshot. Now we have to move further. So that is, I have mentioned code 1 is not a prefix code since the bit 0. The code word for x1 is a prefix of 00 for the code word x3. Likewise, the bit 1, the code word for x2 is also used as a prefix of 11, the code word for x4. Similarly, code 3 is not a prefix code, but code 2 is a prefix code that we have already seen through this discussion. Okay. I hope you have understood this particular concept of prefix coding. That would be used further when we have to go for the Shannon-Pennon coding and the Huffman coding. Now we would be learn one of another concept that is called the average code length. Okay. So I am going to turn on the attendance. You can enter your attendance on the chat box. Now we have to see the concept of the average code length. So we have seen there is an information source that is having the source symbols x1, x2 up to xk, and that would be passed through a source encoder that would be further encoded and generate the code word c1, c2 up to the ck. So for the xk information symbol, that would be a code word ck is there. So you can see that our source information source has the k symbols, and each symbol is here. Each symbol is here having the xk having the probability of pk. This is very important note. Each symbol xk having the probability pk. So each symbol xk is represented by the ck of length lk bits. So code word ck would be represented as a length of lk bits. So now there is a kth symbols. So we have to find out an average code word length. This is very important term, average code word length. So the average code word length L is represented as sigma k is equal to 0 to k minus 1 pk into lk, where the pk is the probability of the each symbol xk that is having the value from the k is equal to 0 to k minus 1, and lk is the length of the each code word. So in this way, from this formula, we can find out the average code word length. In some books or some authors have used the L bar to represent the average code word length. That is also okay. You can use either a term L, capital L, or the L bar. Both are correct for determining the average code word length. So the output, we have to be known the Shannon first theorem. So Shannon, that is also a base of the source coding theorem. So the output of an information source cannot be represented by a source code whose average length is less than the source entropy. This is very important property of the source coding. The output of any information source cannot be represented by a source code whose average length is less than the source entropy. So we can represent with the mathematical equation like this. So the average code word length L should always be greater than the source entropy HFX or equal to source entropy, but it could be never less than this H of X. Okay. Now, one more property and the condition that we have to be remember, the source entropy, so the average code word length should be always greater than or equal to source entropy, but it should be always less than source entropy plus 1. These two are the very important conditions for the further source coding theorem. So note it down, all these two conditions. Okay. And tomorrow we would be see the example of this Shannon's first theorem, and we have to start the Shannon-Fanon coding. So for today, I would be end here because there's less than 1 minute. Only 46 has been be put up their attendance, and already it is shown as the 53 students are present in this particular lecture. So those who are still not mentally connected to this class, please fill up your attendance. Okay, thank you for attending the class today.